I'm going to adopt a holistic approach to mechanics. We looked at a few ideas in mechanics already. Looked at the traits of certain common kinds of forces. I'll introduce yet another force in the midst of our discussion, which is the force of friction. Force of friction. All of you are already carrying some notions about friction. So to give you a basic introduction is a mere formality, just to ensure that you're fundamentally familiar with these ideas. Now, suppose this is a surface and a body rests on the surface. There is a body that rests on the surface. Let's say the surface is a fixed surface to begin with. The forces that are acting on this body, mg downwards and normal reaction from this fixed surface upwards. N may or may not be equal to mg. Depends on whether this is accelerating up or is accelerating down or is remaining fixed. In any case, whatever, let's say fixed surface, it's not even accelerating upwards. If it's not accelerating in the vertical direction, then N would be equal to mg, because there is net of all vertical forces on M must be 0. There is no vertical acceleration of M. Now, imagine that this mass M is connected to this fixed surface by means of these pins. Let's say there are these pins that are connecting this M to this fixed surface. There are these pins that are connecting M to this fixed surface. Now, what do these pins do essentially? When you apply an external force F, then these pins prevent M from having any motion over the fixed surface relative to the fixed surface. These pins ideally would like to prevent small m from having relative motion on this fixed surface, right? That's what these pins would want to do. If you apply a small value of F, then the pins resist to that extent. If you apply a force, let's say F equal to 0.01 newtons, then these pins will apply a force 0.01 newtons in the opposite direction, preventing M from having any relative motion on the fixed surface. Now you increase the value of capital F, then these pins resist even more. For example, now if you apply a force F equal to 1 newton, then these pins apply an equal and opposite force equal to 1 newton, again preventing M from having any relative motion on the fixed surface. Go on increasing F, then the resistance offered by these pins that's going to prevent relative motion between the two surfaces would go on increasing, but not indefinitely. It's not going to happen forever. You can't continue to take liberty with the pins and go on increasing capital F and expect the pins to prevent relative motion between the body and the surface by applying a force commensurate in the opposite direction. After a while, or rather for a certain value of F, when F becomes, let's say, F limiting, when F becomes F limiting, then these pins are on the verge of breaking up. These pins are on the verge of breaking up. They would severe links with M. These pins would break up, would mechanically break up. I mean, if these are pins, they have some mechanical strength, for example, right? So then, their mechanical strength would have reached its maximum value. I mean, in the sense, they can't withstand a force forever and prevent relative motion for a certain value of the applied force. The force that the pins will exert would be the same, but then it would have reached its maximum possible value. Beyond this value of the limiting force, the pins will give in. These pins will start breaking up. And when they are on the verge of breaking up, then the small m is on the verge of sliding on the surface. And this small m is practically on the verge of sliding over the surface. But from F applied force F equal to 0 to F equal to F limiting, from F equal to 0 to F equal to F limiting, then the externally applied force varies from 0 to a certain value F limiting, which would be, this limiting force would be a property of the two surfaces in contact. I'll come to the model that will determine this limiting value of F, right? But in any case, from F equal to 0 to F equal to F limiting, the pins resist relative motion. Their mechanical strength is good enough to withstand the applied force, and this force that the pin exerts to prevent relative motion is a kind-hearted, generous force. And if you are applying a force F equal to 1 Newton, it's not like this force would be more than 1 Newton. It will be just equal to 1 Newton. If you apply 1.5 Newtons, the force applied by the pins will still be 1.5 Newtons. All that the pin wants, all that these pins want is harmony between these two surfaces. The objective of these pins is sheer harmony between small m and the surface on which small m rests. Because the moment there is relative motion, then philosophically you can imagine that to be a state of disharmony, right? So the pins do not want disharmony between small m and the fixed surface, and consequently they resist the externally applied force, but only to a certain extent. When the externally applied force varies from 0 to F limiting, the pins exert a force in the opposite direction, exactly equal to the applied force, so that there is no relative motion between the two surfaces. But like I said, the pins begin to rupture. The moment the value of the limiting force, the moment the value of the applied force exceeds a certain value, this could for example be 10 Newtons. This for example could be 10 Newtons. This limiting F could be 10 Newtons. The moment the value of the externally applied force, for example, exceeds 10 Newtons, the pins begin to rupture. And they can't resist enough to prevent relative motion. That means beyond this value of the externally applied force, the pins give up and they allow relative motion to take place, because the pins would have ruptured by then. But in this regime, F equal to 0 to F equal to F limiting, in this regime of the externally applied force, there are static conditions prevalent between small m and the fixed surface. Between small m and the fixed surface, there are static conditions prevalent. Static conditions means no relative motion. So, and while the externally applied force varies from 0 to F limiting, the frictional force also varies from 0 to F limiting, from instant to instant, countering the externally applied force, maintaining static conditions, right? So, if I designate the frictional force by small f, I mean, what I essentially wanted to tell you was that these pins that I'm talking of are essentially models of the frictional force that we are trying to conceive and trying to build around. Whatever these pins are doing to us is what frictional force would have liked to do. So it was just a conceptual representation of friction. I mean, instead of imagining friction to be abstract, imagine that there are pins that are holding these two surfaces together, preventing relative motion. Friction does exactly the same. So now the force exerted by these pins is essentially like the frictional force that prevents relative motion between the two surfaces. The frictional force F then varies from 0 to F limiting. While the externally applied force varies from 0 to F limiting, the frictional force that varies from 0 to F limiting. And this value of the externally applied force, or this value of the frictional force, which is preventing relative motion, is called static friction. Frictional forces varying from 0 to F limiting. Frictional forces varying from 0 to F limiting is static friction. Static friction. These values of the frictional force are referred to as static friction. Static friction. That means the moment you know that the frictional force between small m and the fixed surface, suppose this is 0 newtons, this is 10 newtons, and through some indirect means you figure out that the force between small m and this fixed surface is 6.1 newtons. Then you can quickly conclude that between these two surfaces there must have been static conditions prevalent. There must be no relative motion between the two surfaces if the frictional force between the two surfaces turns out to be any value between 0 to F limiting. Between 0 to F limiting, you can assume then that static conditions prevail. And conversely, any value of the externally applied force lying between 0 to 10 newtons, for example, will not disturb static conditions between the body and the fixed surface, provided, again, this fixed surface condition is very important because the moment this surface is also mobile, if this surface is also mobile, then the discussion would take a different turn, and whatever I have said would have to be would have to be modified in light of motion or acceleration of the fixed surface. Right? But if the surface is fixed, then values of externally applied force varying from 0 to a certain value would be resisted by these pins that represent the frictional force. Now, when the externally applied force F becomes just slightly greater than F limiting, when the value of the externally applied force F becomes slightly greater than F limiting, are you all there with me on this? Then these pins would have ruptured. And the moment these pins rupture, then they cannot resist that much. The frictional force F now can no longer be F limiting, right? When you applied an external force from 0 to, let's say, 10 newtons, friction continuously varied from 0 to 10 newtons, matching the externally applied force from instant to instant. But the moment the externally applied force became more than 10 newtons, for example, this was 10 newtons, computed in a different manner though. So the moment the externally applied force became 10 newton, the pins were on the verge of breakdown. And now when you applied an external force, let's say 10.2 newtons, for example, then the pins that represent friction cannot resist any further. They break down, and the extent of resistance that they can offer is no longer 10 newtons, will fall to below 10 newtons, will fall to below 10 newtons. That means now the frictional force would be less than F limiting. Would be less than F limiting. The frictional force will no longer be F limiting, it's going to be less than F limiting. And by this time, the relative motion between the body and the surface would have already commenced. And the frictional force between the body and the surface, when relative motion commences, is no longer referred to as static friction, that's referred to as kinetic friction. That's referred to as kinetic friction. So the frictional force value that exists between two bodies that are in relative motion with respect to each other is called kinetic friction. Is called kinetic friction. Got me? So then, to summarize things that I mentioned, let's say this direction represents externally applied force. And on this axis, I measure the frictional force between the body and the surface. This is a fixed surface. This is a body, mg, normal reaction N, externally applied force, F external. So then, when F goes from 0 to a limiting value, when capital F goes from 0 to a limiting value, what you might want to do is, you might just want to plot it a little differently. I mean, because frictional force is varying while capital F is varying, right? I mean, capital F does not depend on frictional force depends on capital F. So just to make the graph look a little neater, you might want to draw frictional force F in this direction. You might want to draw frictional force F in this direction, and externally applied force on which the frictional force depends in this direction, right? So while the externally applied force varies from 0 to a limiting value, small f also varies from 0 to the same value. Small f also varies from 0 to the same value. At each instant, the value of the frictional force matches the value of the externally applied force, as long as the externally applied force lies anywhere from 0 to F limiting. That means, as long as F, the externally applied force, is greater than or equal to 0, less than or equal to F limiting, where F limiting would be a fixed number, and we'll very shortly learn how to compute this reference number F limiting when capital F varies from 0 to F limiting. Small f at each instant will be equal to capital F. Small f at each instant, the frictional force that's preventing relative motion would be equal to the externally applied force, would match the externally applied force from instant to instant, thereby preventing relative motion and maintaining static conditions between the body and the surface. Now, F equal to capital F is a straight line, right? Y equal to X, this is like Y equal to X. This is the Y direction, this is the X direction, this is like Y equal to X. This is a straight line passing through the origin. F equal to capital F is a straight line passing through the origin, and so this is how it varies. This is 45 degrees. So while capital F runs from 0 to F limiting, small f also runs from 0 to F limiting. Runs from 0 to F limiting. And for all these values of the externally applied force, the frictional force exactly balances. The frictional force exactly balances. This is the frictional force. This is capital F, and if this is 45 degrees, then this is equal to this, right? So for any value of F lying between 0 to F limiting, the value of the externally applied force exactly manages or balances, or rather the frictional force balances the externally applied force. Now, all these, so then, while capital F varies from here to there, how many values of frictional force exist? Any number of values of frictional force lying between 0 to F limiting, right? And these values of the frictional force lying from 0 to F limiting are called static friction values, These values of the frictional force are referred to as static friction values. These are referred to as static friction values. That means two things could be concluded. Number one, if the value of the frictional force calculated, let's say indirectly, turns out to be anywhere from 0 to F limiting, you can conclude that between the body and the surface, there couldn't have been relative motion. And conversely, if there is no relative motion between the body and the surface, then the frictional force must lie anywhere from 0 to F limiting. Got me? So this is static friction. This is the region or regime of static friction. Now, the moment the externally applied force surpasses this value, just goes slightly more than this, then like I said, the pins that represent the frictional force, the pins will break down, and the moment the pins break down, then the frictional force or the capability of the pins to resist motion will decrease. The capability of the pins to resist motion would decrease. Up to this point, all right, the frictional force and the externally applied force was the same. But the moment the externally applied force just increases to beyond this value, the pins will break down and the frictional force will decrease. Right? That means just slightly beyond F limiting, what really happens is the frictional force decreases. And by this time, relative motion between the body and the surface would have already commenced. The frictional force would have fallen below this maximum value. And after it has fallen by a small amount, it remains practically constant after that. Right? And this constant value of the friction force, that occurs between two bodies between which there is relative motion is called kinetic friction. This is F equal to Fk. Which is kinetic friction. Frictional force between a body and a surface when there exists relative motion between the two, that's kinetic friction. And this F limiting is static friction, but the largest possible static friction. This is the largest possible static friction. This F limiting is largest static friction. That means this is the maximum value of static friction possible. Sometimes also referred to as maximum static friction. This is called maximum static friction. The maximum value of the frictional force possible between two surfaces having no relative motion with respect to each other, that's called maximum static friction. And this is kinetic friction, and that happens when there is relative motion between the two surfaces. When the externally applied force is such that the relative motion would have commenced between the two surfaces, then the force of friction prevalent is kinetic friction. Then no matter, once relative motion has commenced, then no matter how much you increase F, the kinetic friction value remains practically constant. Now, how does one compute this F limiting value? That is the maximum static friction. That's the maximum static friction. Let's say there is a fixed surface. This F limiting is commonly written as F max stat. Maximum value of static friction, small f, maximum static. Now, to be able to compute the maximum static friction between a body and a surface, there are empirical models available. These models are obtained out of experiment. They're not obtained theoretically, it's done mostly experimentally. Now, in a lesser sophisticated sense, the simple model of friction suggests that if these two bodies are pressing hard against each other, if the fixed surface and this body, if they are pressing hard against each other, that means pressing each other is measured by what? Two bodies pressing each other is measured by what kind of a force? Normal force between the two surfaces, right? The normal force between two surfaces is a measure of how intensely they are pressing against each other, right? The normal force. So now empirically it's been found that the harder they press against each other, the greater will be the value of maximum static friction between the two surfaces. The harder they press against each other, the greater would be the value of this limiting force, or the maximum possible value of static friction between the two surfaces. And like I said, the force that they exert on each other is measured by N. The extent to which they press each other is measured by the normal reaction between the two surfaces. So it's been found that this maximum static friction force is proportional to the extent to which they press against each other, that is the normal reaction between the two surfaces. And that is some constant times n, and that constant is referred to as mu s, coefficient of static friction. That constant is referred to as mu s, or the coefficient of static friction. The value of this mu s will depend on the nature of the surfaces in contact. Will depend on the nature of the surfaces in contact. If the two surfaces in contact have less number of undulations, those undulations actually are like those pins that I drew for you, those pins that create interlocking between the body and the surface, right? Those pins are actually a measure of the undulations, because those undulations act like pins interlocking the body with the surface, right? So nature of the surfaces means the number of undulations present on the two surfaces in contact. If you lessen the number of undulations on the two surfaces, then we say that the two surfaces have become smoother, and then the value of mu s decreases. The value of mu s decreases because there is lesser amount of interlocking. If those undulations are less, then between the body and the surface there would be a lesser extent of interlocking, and this mu s decreases. So then this is computed out of experiment. This mu s is not computed theoretically, it's computed out of experiment. So if you have a body and the surface, then you compute this mu s experimentally once and for all. You can use it repeatedly. But then this n is not a constant for the body and the surface. This mu s, if I have not tinkered with the quality of the surfaces in contact, then this mu s will not change its value. But this n does not depend on the undulations or the nature of the surfaces in contact. It will depend on the larger scenario of forces acting on the rigid body. N in general, for example, in a situation like this, there is N acting upwards, mg acting downwards. N acting upwards, mg acting downwards. And if there is no vertical acceleration of small m, if this a vertical is 0 for small m, then the net of all forces in the vertical direction acting on m must be 0, and then becomes 0, right? But if the acceleration in the vertical direction is not 0, then I have like a n minus mg as the net vertical force acting on small m responsible for creation of AB. So then this must be m times the vertical acceleration. So then n is no longer equal to mg, n becomes m into g plus AB. So the same two surfaces in contact, but a different value of n. And if a different value of n, that means the maximum static friction would become different if you have a different value of n. This mu s will not change if you are not licking the surface, not eating it up or doing lousy things with the surface. Mu s would remain constant, but n could change depending on other forces acting on the body. This n could be different. For example, if one had a situation like this, there is mg downwards, there is normal reaction n upwards, and let's say there is a downward force acting on this rigid body, pressing this rigid body, and this is a fixed surface. In this case, n will no longer be equal to mg. If there is no net vertical acceleration, and if you apply an external force downwards, then in the vertical direction, if there is no acceleration, then we must have Fd plus mg minus n equal to. So then now again n has changed, right? Because there was a force Fd acting. Between the same pair of surfaces, the normal reaction changes. So maximum static friction would also change its value commensurate. Similarly, if one had, say, if I applied a force F like this, and this was a fixed surface, and if this was a fixed surface, right, and let's say this F made an angle theta with the horizontal, then this F could be resolved as F cos theta, and f sine theta. Right? This f could be resolved horizontally as f cos theta and vertically as f sine theta. And then there is mg acting downwards, there is normal reaction n acting upwards, and if this was a fixed surface, means there was no vertical acceleration of this surface, then the normal reaction would be computed as f sine theta plus mg minus n equal to 0. This would make the new value of n available to you. Right? So then, the value of n will depend on other forces acting on the body, and so it will not be, it's not a fundamental trait of the pairs of surfaces in contact. It's not a fundamental trait of the pairs of surfaces in contact, whereas mu s is fundamental for the same pair of surfaces, irrespective of the value of n that exists between the two surfaces. Mu s will remain unaltered, unchanged. Got me? So that's how one computes the maximum static friction between a body and a surface. The kinetic friction again, which is the frictional force between a body and a surface when there is relative motion between the two. This kinetic friction is the frictional force between the body and the surface. In the event there is relative motion between the body and the surface, then this kinetic friction again empirically has been found to be equal to some constant which is called mu k. Instead of mu s, it's called mu k into n, where n would be computed based on all of the forces acting on the body and the state of the body, where mu k would be a fundamental property of the nature of the surfaces in contact. It would depend again on the extent of undulations and is experimentally computed. Mu k. This mu k is called coefficient of kinetic friction. Called coefficient of kinetic friction. And it's been found, and as you would also expect logically, since kinetic friction is less than maximum static friction, this is maximum static friction. These are all static friction values, but this is maximum static friction. Since maximum static friction is larger than kinetic friction, you would expect mu s to be larger than mu k. You would expect mu s to be larger than mu k. Again, found experimentally, the difference between mu s and mu k is not significant. It's very, very small. This dip in the frictional force, when the externally applied force goes slightly beyond F limiting, this dip in the frictional force is really very, very small. Very, very small. As a result, the transition from mu s to mu k is not significant. So, only when the situation is very sophisticated do we take mu s and mu k as different. But if somebody has prescribed only mu s to you, then, and if you still need kinetic friction values, then you can take mu s to be approximately equal to mu k. That's a good enough approximation. If somebody has given you only mu s, but you want to compute Fk, kinetic friction, then for all practical purposes, you can take mu s to be approximately equal to mu k. That's a good enough approximation. Again, it might seem that when a body is in contact with a surface, the maximum static friction, as you can see here, depends only on two things. It depends on the normal reaction between the two surfaces, body and the surface, and it depends on the value mu s and nothing else. And mu s is fundamental, so it's once and for all, it's like a constant. So it depends only on the normal reaction. It might then seem that if the body is in contact with the surface, then the area of contact will not play a role in determining the frictional or the maximum static friction between the body and the surface. Now again, this statement is an approximation. In fact, maximum static friction depends also, although to a lesser extent, it does depend on the area of contact. It's a weak function of the area of contact. So when the application is very sophisticated, then the dependence of frictional force on the area of contact would also have to be accounted for. However, if the application is not very sophisticated, then assuming that the frictional force does not depend on the area of contact between the body and the surface is a legitimate one. One can go ahead and carry out calculations based on this assumption. But it does depend on the area of contact, although it's a very, very weak function of the area of contact between the body and the surface. Now, like I've said, the objective of this frictional force is only to prevent relative motion. Be it kinetic friction or be it static friction. As far as kinetic friction is concerned, it's an easier thing to deal with because it has just one value, mu k into n. There is just one value available for kinetic friction, which is mu k into n. But static friction has many values, starting anywhere from 0 to that f limiting. Static friction can have any number of values, right? So if between the body and the surface there is no relative motion, then the frictional force between the two could be anywhere from 0 to f limiting, right? So it's like groping in the dark. We do not know exactly what it is till such time that we investigate it further. But if I know that there is relative motion between the two surfaces, let's say this has a velocity 5 meters per second and this surface has a velocity 10 meters per second. Suppose this upper body has a velocity 5 meters per second, the fixed surface has a velocity 10 meters per second. Then there is relative motion between the body and the surface. If you are standing on this surface 10 meters per second, if you are standing on the surface that has motion 10 meters per second, then what would you perceive? And as far as the velocity of this is concerned, 5 minus 10, which is minus 5 meters per second. That means minus 5 meters per second in this direction means 5 meters per second in this direction. So if you are an observer resting on the surface, if you are an observer, you couldn't be resting because it's moving, right? But in any case, if you are an observer on the surface, you would find this to be having a relative velocity of 5 meters per second leftwards. This would be found to have a relative velocity 5 meters per second with respect to the surface. Now, that means the moment this surface identifies that this body has a relative velocity of 5 meters per second leftwards, what friction does is, friction acts in this direction. Friction on this body would act in this direction, and the nature of friction is kinetic, and the direction is this. The direction of the frictional force acting on a body would always be opposite to the direction of relative velocity, not the velocity, would be opposite to the direction of the velocity, relative velocity, not the velocity. See, even though the velocity of this body as seen by a ground observer is 5 meters per second to the right, the relative velocity is leftwards with respect to the surface. So frictional force acts in a direction opposite to relative motion, not in a direction opposite to motion. It will act in a direction opposite to relative motion. An observer here finds that this surface has a relative velocity 5 meters per second leftwards. So frictional force acts in on this body acts in a direction opposite to the relative velocity of this body. So frictional force is not averse to motion. As you can see, it's favoring motion. It's favoring motion, right? It's only averse to relative motion. It's averse to relative motion. It says, all right, I don't care. If this moves with 10 meters per second this way, and this moves with 10 meters per second this way, then frictional force stays quiet. It doesn't even act. Even though there is motion, of this body. This body has motion, 10 meters per second. But then there is no relative motion of this body. So frictional force is not going to act. Frictional force is not going to act. Frictional force will act. In this case, the frictional force is 0. Right? If this has a constant velocity of 10 meters per second and this has a constant velocity of 10 meters per second, then there is no relative motion and there would be no frictional force. But in this case, the relative velocity at this instant is 5 meters per second. So frictional force on the upper body would be to the right. Now who exerts this frictional force F rightwards on this body? The surface. So then, why should third law fail here? The body would respond to the action of this F. This body would exert on the surface a small f in the backward direction. On this surface, a small f would act backwards as a response to this f. Right? This f is exerted by this surface on this body, whereas this f is exerted by this body on this surface. Right? They constitute a action-reaction pair. Fair enough? So, frictional force acts in a direction. Kinetic friction, in fact, let me say, I'm talking of kinetic friction right now. Kinetic friction is easy to judge. The moment you figure out the direction of relative motion, you know the direction of kinetic friction. The magnitude of kinetic friction is unambiguous. There is just one value of kinetic friction, which is mu k into n. Mu k would be a property depending on the nature of the surfaces, which would be given to you, and could be computed based on other forces acting on the body. Right? So, it's easier to deal with kinetic friction. But when it comes to static friction, you know that it could be anywhere from 0 to F limiting or maximum static value. And again, the direction of static friction, that would sometimes, as you figure out while we experience situations on friction, you'll figure out that the direction of static friction is not always as easy to figure out as is the direction of kinetic friction. The kinetic friction is as easy as I suggested, but the direction of static friction could get a little trickier. One more thing, which I want to, and I'll talk about, how it could get a little trickier. Let's go past the basics first. One more misconception that people carry because they are plagued by what they have read in books is the following. If this is a surface, and this is an externally applied force, and F limiting, which is the maximum value of static friction between these two surfaces, F stat max is F limiting, that I have been talking of. This can be computed, mu s into n. Now, one very popular misconception that is carried very, very far by people, sometimes carried forever, is the following. Suppose this turns out to be 10 newtons. On calculation, this mu s into n turns out to be 10 newtons. Then most people and most books will come up and tell you the following. They'll say, well, the minimum value of F that you must apply on this so that relative motion just about commences is 10 newtons. The minimum force, externally applied force, that would cause relative motion is 10 newtons. They would very often come up and say that the minimum value of the applied force that would cause relative motion is maximum static friction. For the time being, I want you to write this statement with a clause. Please make a note of it. I'll add a clause to it, and very, not, if not today, but maybe in my subsequent problem solving sessions, I'll demonstrate what I actually meant. But for the time being, just make a quick remark around this. The minimum F that could cause relative motion, equals maximum static friction only when the surface on which the body is resting, is quote unquote unaccelerated, when this surface is unaccelerated, only then can I claim that the minimum F required to cause this to just about slide on this is F limiting or maximum static friction. Otherwise, this statement is rubbish. I mean, I'm sure you have read some friction in school or some friction in books. Have you? Right? In which it's stated very conventionally that the minimum F required to cause sliding is maximum static friction. The minimum value of the externally applied force should be maximum static friction, but that's true only when this surface is unaccelerated. If this surface is itself accelerated, then the statement is rubbish, right? Then the minimum F required to cause this to accelerate or to slide over this is no longer maximum static friction. I would illustrate that fact. But for the time being, just keep it in your mind. Now, let's say this is capital M, this is small m, and let's say this is a smooth surface. Let's say this is a smooth surface. And the system starts from rest. It's initially at rest. The whole thing is at rest initially. And let's say the coefficient of static friction between small m and capital M is μs. The coefficient of static friction between capital M and small m is μs, which would be served to you on a platter. Somebody will tell you the static friction value between coefficient of static friction between small m and capital M would be given to you. Now, let's say you apply an external force F on the lower body. Suppose you apply an external force F on the lower body. Alright. And let's say this surface is not just smooth, it's also fixed. Let's say this surface is not just smooth, but is also fixed. Right? Now, how would I know whether small m and capital M have relative motion between the two? Whether capital M and small m at all have relative motion or not? Okay, if I can figure out the frictional force between small m and capital M, and if that turns out to be less than maximum static friction, if I can figure out indirectly the frictional force between small m and capital M, and that turns out to be less than maximum static friction between the two, then I know that there is no relative motion between the two surfaces. Yes or no? You know what I'm saying? Each time you want to figure out whether there is relative motion or not, you assume that there is no relative motion. Each time you want to figure out whether there is relative motion or not, you assume that there is no relative motion. And at the end, if you arrive at a contradiction, then you can assume that your assumption was incorrect and there indeed was relative motion. You start with the premise that there is no relative motion. You start with the premise that there is no relative motion. Say no relative motion. If there is no relative motion and they start from rest, that means small m and capital M must have a common acceleration, So that means, let's say capital M and small m have a common acceleration a to the right. Must have a common acceleration a to the right. See, like I said, this is a situation where if I know for sure that there is relative motion, I can figure out, or if I know for sure the direction of motion of this and direction of motion of this, then I can figure out the value of the frictional force, the direction of the frictional force. But in a situation where static conditions prevail between the body and the surface, frictional force could still be there, but the value of the frictional force could be anywhere from 0 to a maximum permissible value, right? So that becomes a stickier situation to deal with. So you assume that the body and the body small m and the body capital M have a common acceleration a, and that there is no relative motion between them. If that be the case, well, then the frictional force that capital M exerts on small m and small m exerts on capital M are equal and opposite. And if you look at small m and capital M as one single unit, then the frictional force is an internal force and that will cancel off in pairs, right? So then the acceleration, the common acceleration is like F by capital M plus small m. F by capital M plus small m. That would be the common acceleration of the two masses. Now, let me look at the free body diagram of the upper mass alone. Let me look at the free body diagram of the upper mass alone. What are the forces acting on the upper block? There is mg downwards, and there is normal reaction that capital M exerts on small m upwards. There is normal reaction that capital M exerts on small m upwards. And the net effect of all forces, I have not yet put up all the forces on small m. Small m also experiences a frictional force from capital M, whose direction I would represent in a while. But before that, let me see what is small m doing. After all, if small m is sharing a common acceleration with this, then you must represent the acceleration a of small m to the right, right? Now, what would cause small m to get accelerated to the right? A force in the rightward direction? A force in the rightward direction would cause small m to get accelerated rightwards. Now, mg is not to the right, n is not to the right. What's the only force that could be acting on small m to the right? Frictional force. frictional force is the only force that could be acting on small m to the right, producing in small m an acceleration a, which means the frictional force acting on small m must be rightwards. Frictional force acting on small m must be rightwards. And who exerts this frictional force on small m? Capital M. Capital M exerts this frictional force on small m, which is F to the right. Okay. Now A has been computed. Capital F by capital M plus small m. This A has been computed. And we are assuming that there is no relative motion between the two surfaces. Right? So then, what would F turn out to be? F would turn out to be small m into A. F would turn out to be small m into A. Right? Now, once you compute this small m, A you have computed, small m you knew, so you've been able to compute the frictional force between capital F and between capital M and small m, so that the two blocks move harmoniously to the right. Yes or no? And let's also compute maximum static friction between small m and capital M. Let's also compute maximum static friction between small m and capital M. Okay. Now, if n is the normal reaction between small m and capital M, then in this case, there is no vertical acceleration. So, n turns out to be equal to mg. N turns out to be equal to mg. So then, what is F max stat, maximum static friction? Mu s would be given to you. What is maximum static friction between the two bodies, to the block, between the two blocks? Mu s into n, mu s into n. Okay, now you have two numbers with you, right? You have this number, which is maximum possible static friction between the two blocks, right? And you have this number, which is the frictional force that acts on small m, right? And what have you assumed? You have assumed that between small m and capital M, static conditions are prevalent. You have assumed that between small m and capital M, static conditions are prevalent, right? Static conditions prevalent means that could have happened only if small m was less than or equal to F max stat, right? Suppose this turns out to be 3 newtons and this turns out to be 10 newtons. Then your assumption is correct. If suppose this turns out to be 3 newtons on calculation and this turns out to be 10 newtons, then the force of friction between small m and capital M is less than maximum static friction. That means between small m and capital M, static conditions are prevalent. So the frictional force should have been less than this, which is what happens. And your assumption of a common acceleration of the two masses is justified, right? But suppose this turns out on calculation to be 10 newtons and this turns out to be 10.8 newtons. Then how can the frictional force between the two bodies exceed maximum static friction? It can happen if your assumption is wrong, right? Your assumption about prevalence of static conditions between the two blocks is incorrect. Which means the two blocks must have had different accelerations. They could be moving together. And then life becomes easy. Once you know they have different accelerations, then the force of friction between them is fixed. It's kinetic friction. It's mu k into n. It's, right? Suppose this turns out to be 10.8 newtons, I said, and this is 10 newtons. That means the force of friction exceeds the maximum static friction, which couldn't have happened. That means the static conditions between small m and capital M never existed, right? And if they never existed, there must have been relative motion between the two blocks. And if there was relative motion between the two blocks, then the force of friction between the two is uniquely defined, and that's going to be mu k into n, which is approximately equal to mu s into n, which is approximately equal to mu s into n, right? Are you all okay with this understanding? So then, the required condition for small m and capital M to move as a cohesive unit. What's the necessary condition for small m and capital M to move as a cohesive unit, maintaining static conditions with each other, is that small f must be less than or equal to maximum static friction. How about this? Right? So then, to move cohesively, f must be less than or equal to f max stat. F must be less than or equal to f max stat. Right? But what is f? F is m into a. A means capital F by capital M plus small m. Right? So then, m into f by capital M plus small m, that's f, as we've computed, right? That must be less than or equal to mu s into n, where n for this situation is mg, where n for this situation is mg, because there is no vertical acceleration. N minus mg is 0 because small m has no vertical acceleration. However, if the whole system was placed in an elevator having a vertical acceleration of 3 meters per second squared upwards, then n minus mg would be equal to small m into 3. N would then be different from mg, right? But in this case, if there is no vertical acceleration, n equals mg. Is that okay? Right? Which means m into f by capital M plus small m is less than or equal to mu s into mg, right? So f less than or equal to mu s into g into m plus small m. Means what? That this really gives me the condition, this inequality gives me the condition required to maintain static conditions between small m and capital M. This is the mathematical requirement. This is the mathematical requirement towards maintenance of static conditions between small m and capital M, which means what is capital M? The externally applied force acting on capital M, that should not exceed this value. That should not exceed this value if you want small m and capital M to move harmoniously and together. If the value of the externally applied force exceeds this number, then small m and capital M would move with different accelerations. They would have relative motion with each other. They would have relative motion with each other. Yes or no? Now again, now instead of applying the force on the lower block, let me next apply the force on the upper block. Let's say mu s is given to me, and this surface is fixed and smooth. Now, I next want to figure out if the two blocks move together or not. With this value of the externally applied force, which would be given to you, F equal to 40 newtons, 100 newtons, somebody would give you the value of the externally applied force. Mu s would be made available, and you then want to be able to compute or figure out if there is relative motion between small m and capital M, or if there is no relative motion, what's the common acceleration, right? So, like I've told you before, you always assume that there is common acceleration, right? That means if you're assuming there is common acceleration, you assume that there is static conditions prevalent between small m and capital M. That means you're also assuming that the frictional force between small m and capital M is less than or equal to maximum static friction between the two, right? That's what you're assuming. So then, assumption of common acceleration leads to A, the common acceleration equal to F by capital M plus small m. A equal to capital F by capital M plus small m, that's the common acceleration, if at all. So this is all hypothetical. Now, let me look at the lower block. This is the lower block, mass capital M. The forces acting on the lower block are like mg, downwards. Normal reaction R from the ground upwards. From the ground there is normal reaction upwards, and small m presses against capital M with a force equal to capital M. Right? This is the free body diagram of capital M. Not all forces have been included yet, but let me first include what's happening on capital M, the effect. The effect of all forces acting on capital M is a common acceleration A to the right. Right? We're assuming that the two blocks have a common acceleration A to the right. So on capital M, there is an acceleration A to the right. Right? Now, what would provide the acceleration A to the right to capital M? It has to be frictional force. That means small m must exert on capital M a rightward frictional force. Small m must exert on capital M a rightward frictional force. Small m exerts, and it is this F acting on capital M that produces this A on capital M. Is that okay? So can I say that capital F, small f is capital M into A? Small f is capital M into A. Could that be said? Where A is computed from these considerations. Okay. Now, what's the maximum static friction between the two? Maximum static friction between small m and capital M, computed again independently, is going to be mu s into normal reaction between this pair of surfaces into n, mu s into n. N is the normal reaction between small m and capital M. So mu s into n. Right? Okay. Now once you have carried this calculation out, this number, suppose it turns out to be 15 newtons and this number turns out to be 6 newtons. Then is your assumption good or bad? Suppose this maximum static friction between the two surfaces turns out to be 15 newtons and this is the actual value of the frictional force between the two surfaces. This turns out to be 6 newtons. Then is your assumption good or bad? Good. Because you had assumed that there is prevalence of static conditions between the two. Commensurate with that assumption, you got the frictional force between the actual frictional force between the two surfaces not exceeding maximum static friction between the two surfaces. That means your assumption was good, right? But suppose this is 15 newtons, and when you calculate this turns out to be 16 newtons. Then is your assumption good or bad? Bad. Because you had assumed static conditions between the two. That means what you should have arrived at is the actual frictional force not exceeding maximum static friction between the two surfaces, right? But if this exceeds maximum static friction between the two surfaces, then your assumption of common acceleration between the two surfaces or your assumption of no relative motion between the two surfaces is incorrect, right? So then, for no relative motion between small m and capital M, what would you expect? You would expect F to not exceed F max stat. You would expect F to not exceed F max stat, right? What is F? F is capital M into A. F is capital M into A less than or equal to maximum static, which is mu s into, now between small m and capital M, look at the free body diagram of small m. If you look at the free body diagram of small m, what are the forces acting on it? Mg downwards, and there is normal reaction N upwards. So if there is no vertical acceleration of small m, N is equal to mg. So the same N small m exerts on capital M. That means this N is small mg, not capital Mg, but small mg. So less than or equal to mu s into N, that is small m into g. Maximum static friction is mu s into small mg, right? Right? So this must be the condition to be met so that there is no relative motion between the two surfaces and the force of friction between small m and capital M is within its limiting value, right? Within its limiting value. So capital M into A like we've seen is capital F by M plus small m. Less than or equal to mu s into mg, right? So we have F less than or equal to mu s into mg into capital M plus small m by capital M. If the value of the externally applied force does not exceed this value, that means there is no relative motion between the two surfaces. The two surfaces are moving together and all your assumptions are correct, right? So you can compute this. Suppose this turns out to be 80 newtons, and if F is 60 newtons, that means this condition is met. That means there is no relative motion between the two bodies and they indeed have a common acceleration. And thing that I stated is, means what? The moment F exceeds this value, there would be relative motion between the two surfaces, right? The moment F exceeds this value, there would be relative motion between the surfaces. Now in this case, the minimum value of F required to cause relative motion between the two surfaces is this. Because if F becomes just larger than this, there would indeed be relative motion between the two surfaces. But is this maximum static friction between the two surfaces? No. Because maximum static friction between the two surfaces is mu s into mg. So that statement about the minimum force required to cause relative motion between the two surfaces must be maximum static is junk. See, maximum static friction between the two surfaces is still mu s into mg. But the minimum F required to cause small m to slide over capital M is not mu s mg, is this, which is not mu s into mg. That's what I meant when I stated that fact. Right? The minimum value of the externally applied force required to cause one body to slide over another body is not necessarily equal to maximum static friction. In this case, realize that this had an acceleration. If this had zero acceleration, if this was a fixed surface, all of a sudden you held it in place. Then the minimum F required to cause small m to slide over this would be mu s into mg. But if capital M had the flexibility to accelerate, then the minimum value of F required to cause small m to accelerate on capital M is not mu s into mg, but is this. You'll bear with me on this.